Hi, and you're welcome to topic 3, which is going to be looking at estimation. As a general, we're going to be looking at the estimation of population parameters, but today I'm going to be focusing on the estimation of a population mean, and then I'm going to move very briefly to the estimation of a population proportion. So recall what we did previously. We talked about taking a sample from a population, and then once we had the sample, we got a sample average, for example. So we looked at the average level of moderate to vigorous physical activity based on a sample of 200 people in the Mitchellstown cohort. And then I talked about how in the second week we talked about how you need probability theory to get you from the population to the sample. But then if you want to say something about the population based on what you see in the sample, then you need probability theory again, because you need to take account of the fact that the sample average is only an estimate of the population mean. And in order to capture the fact that it is only an estimate, and the fact that if you took repeated samples it would vary, then you need to think about the probabilistic nature of that sample average. And that's what we're going to do today. So you need to recall something from the very first week when we talked about the normal distribution. So you'll recall that what we mentioned with the normal distribution was that it was centered at the mean value, but that clearly it varied from person to person. And we talked about this fact here, that if it was normally distributed, then we would expect 95% of people to lie within approximately 2 standard deviations of the mean value, so that the standard deviation was a measure of the spread, and in particular was the spread from one person to the next. And keep in mind that one fact as we go along, that 95% of people lie within 1.96, or if you prefer 2, standard deviations of the average. Now at this stage I want to do a demo using Stata. It's similar to what you saw in the SCORM where you used online software, and there's also up in Blackboard a longer version of this. So I just want to go through a brief demo here. So the first thing I want to illustrate is how estimates vary. That is to say, if you take a sample average, for example, you will get one value, and if you take sample averages repeatedly, you will get different estimates each time. So this is a cut and paste out of Stata. So what I've done is I've taken a normal distribution, and you can see that on the distribution type. So we've taken a normal distribution, and we've basically sampled one person, and then we've sampled another person, and then another person, and we've done that 1,000 times. So what you have here is a simulation of a situation where you're sampling 1,000 people. You're sampling them from a standard normal, which says in essence that the mean value should be 0, and the standard deviation should be +1. And that means that from that original rule we were just looking at, that we would expect 95% of the people to lie within -2 and +2. That is to say, the mean -2 standard deviations up as far as the mean +2 standard deviations. And that appears to be reasonably the case here. So we have something which the histogram is reasonably bell-shaped, as it should be, because we're sampling from a normal. And you can just about see that bell curve actually fits it pretty well. Now imagine what happens if we were to take an average. I've highlighted the 100 there in terms of the number per sample. So what we're looking at now is a situation where we take 100 people at random from the population and we get a sample average, and then we repeat that 1,000 times. So now we're not looking at the distribution from person to person, rather we're looking at the distribution from one estimate to the next estimate, from one sample average to the next sample average. And notice that the shape is still bell-shaped, but also notice that area that I've highlighted down on the horizontal axis, because before it went from -2 to +2 for about 95% of people. Now it's going from about -0.2 to +0.2. You may notice that that's actually dividing by 10, which actually links in with what you heard about the square root law way back. So when we take samples, if something was originally normal, it continues to be normal. It continues to be centered around the population mean, which in this case is 0. but the spread falls. So ultimately something that is normal continues to be normal, but the variation in the sample averages is less than the variation that you see from one person to the next. Now we move on to the central limit theorem, and with no pun intended, central limit theorem is central to everything that we do when we talk about estimation, and it will also be central to everything that we do when we talk about inference. So in order to demonstrate the central limit theorem, what we need to do is we need to look at a situation where we have a distribution which isn't normally distributed. So this is a particular example. It's again using Stata. It's again using a command called CLT in Stata, and the other video actually explains exactly how you use that. But what matters is we have a distribution. It's certainly not normally distributed. You can see it has a huge tail on it. The nature of a log normal distribution is such that it can never go negative. And the kind of things that tend to have log normal distributions are usually time variables. So it might be how long you spent in a hospital, for example. It might be a waiting time. So we have something. This corresponds to taking 1,000 people at random from that population and then producing a histogram. And this is what we see. And as you go along, keep your eye on that area that I've circled down the bottom so as to capture the spread. So at the moment it goes from about 0 up to maybe 17, and most people are packed between about 0 and 3. Now look at what happens if we take an average of 5 readings. So we take 5 people at random from the population and we get the sample average for those 5 people, and then we repeat the process 1,000 times. We get 1,000 sample averages, and then we get a histogram of those 1,000 sample averages. And look at what's happened. The distribution is now not as spread out as it used to be. It's only going up to, the maximum now is up around maybe just over 9. And the distribution, if you look at the shape of it, it's certainly not normal, but it's not as skewed as it was previously. And that's only based on 5 readings. If we go to 10 readings, the spread gets even tighter. Still not quite bell-shaped, but it's starting to get there. It's hard to tell this, but it's actually centered in the same place each time. So it tends to be centered in the same place. The spread is getting narrower, and it's getting more and more normally distributed as we take larger samples. This is what happens if we go up to 20 readings. So we're taking a sample of at random of 20 people, we're getting an average, and then we're repeating that process on 1,000 times. So this represents the distribution of the sample averages. And the same thing again, the spread is reduced and it's becoming more bell-shaped, more normal. This is what happens if we go up to 100 readings. So it's even better now. The spread is even tighter than it was before, and the distribution is becoming even more normal. And then just to capture this, the one that's listed as raw data there, that's the original sample that we looked at. So that represents the variation from one person to another. And then the other histogram, the one in funny shaded grey, actually represents the distribution of your sample averages. So the grey histogram is saying if you took a sample of 100 people and got an estimate and then repeated that 1,000 times, this is what the distribution of the averages would look like. And the green histogram is saying if you just looked at the distribution from one person to the next, this is what the distribution would look like. And the central message in all of this is that as you take large samples, the distribution of your estimates start to become normal, even when the distribution from one person to the next isn't normally distributed. So then, if we were to try and summarize what message we get out of that demo, we see that first of all the estimates vary. They vary about the true population value. That was obvious when we were looking at samples from a normal distribution, perhaps not so obvious when we were looking at samples from a log normal, but they cluster around the true population value. The variation that you see falls, that's to say the variation in your estimates fall as you get larger samples. And clearly the less they vary the better. If they're tending to cluster around the population value and they don't vary very much, then you're getting precise estimates of the population value. And the larger you make the sample size, the more precise those estimates become. And then finally there was the fact that the distribution of the estimates becomes approximately normal. So the distribution in this case of the sample averages, although it's more general than that, but the distribution of the sample averages in this case becomes approximately normal. And we then talked about the fact that the estimates vary. And then just to get the terminology straight, when we talk about variation from one person to the next, then we talk about a standard deviation. And when we talk about the variation from one estimate to the next, we talk about what's known as a standard error. It's just terminology so as to separate the idea of the variation person to person from the variation from one estimate to the next. The error doesn't mean that there's something wrong in the method in which we take our sample. It simply means that our estimate is not equal to the population value. And again, precise estimates have small standard errors, and the larger the sample, the smaller the standard error. And as you might guess at this stage, you're going to find that 95% of the estimates will lie within 2 standard errors of the population value. Now, just to bring that home, if I was to ask you to calculate the standard error, then the reality is you'll never have to calculate it because you're going to be using software, but it's good to have the formula because it just illustrates the theory. So what we have here is the standard error. Remember, the standard error is the variation that you see in your estimates. And the standard error is equal to the standard deviation, which is the variation that you see from one person to the next, divided by the square root of the sample size. So previously, when we had something with a standard deviation of 1 for the standard normal, and then we had a range from -2 to +2, and we took a sample of size 100, so that the square root was 10, we found that the variation for 95% of our estimates was from about -0.2 to +0.2. And as I mentioned, that's what's known as the square root law. And what all that tells you then is that clearly the standard error goes up with the standard deviation, it falls with the sample size. So let's return to an example then. This is from the Mitchellstown cohort. It's from the database that you have, so you should actually be able to replicate this, and it's well worth replicating this one. I should have mentioned it's also well worth replicating the CLT command, just to show yourself that this actually works. So this is the distribution of moderate to vigorous physical activity. It's measured in minutes. It's the number of minutes of what we will class as moderate to vigorous physical activity over a 24-hour period. And when you look at that, you should find that the mean value is 338 minutes. The standard deviation is 163. And that tells us that if it's truly normally distributed, then 2/3 of people will lie within 1 standard deviation, which is to say within 163 minutes of the average, and 95% will lie within 2 standard deviations, which is 326. So the standard deviation is capturing the variation from one person to the next. Now if we do that and we say, okay, we have 200 people, and the standard error is the standard deviation divided by the square root of 200, then if I've done the maths correctly, the standard error will be 11.5. And that means that we would expect that 95% of our estimates will lie within 2 standard errors of the true value. And you can turn that around and you can say that you don't know what the true value is, but you expect that, or rather, let me rephrase that, you're confident that the true value is within 2 standard errors of your estimate. So if we take our estimate, which is the population mean, and then we add and subtract 2 standard errors, we get that 95 CI, which is the confidence interval, which is 315 to 361. And notice what that depends on. It depends on our estimate, 338. It depends on the fact that it's a 95% confidence interval, which is why we're adding and subtracting 2 standard errors. And the standard error depends on the standard deviation, which is the variation person to person. And we don't control that one. but it also depends on the size of the sample, which is the 200, and we do control that. Now this is just some output from Stata. This output is basically illustrating the points that I made previously. So we have our sample of 200. These are the Stata commands up here if you'd like to replicate this. So we have a sample of 200. This is the mean. This is the standard deviation. On the previous slide I just rounded everything up. So that's using the sum command, or if you like the summarize command. And then if we use the mean command, which you saw demonstrated in the SCORM, if you use the mean command, then it gives you the estimate, which is 338, which is the same as the sample average. It gives you the standard error, and the standard error should be the mean value divided by the square root of 200. And it's an estimate of the precision of the mean as an estimate of the population. And then it gives you a confidence interval here. And that confidence interval is approximately the mean plus or minus 2 standard errors. So what exactly is a confidence interval then? Because I kind of rushed past it previously. Well, a confidence interval is an interval, naturally, and it's an interval in which you're very confident the population parameter lies. In this case, parameter is the population mean. So it's worth nearly stating that a few times. So the idea is that the population parameter does not vary. The population parameter is not varying. There's a certain average level of moderate to vigorous physical activity for the population that Mitchelstown is sampling from, and that doesn't vary. But when you take a sample, the sample estimates vary. And on the one hand, you can say the estimates are varying around the population mean. In that previous example in the SCORM, when you were talking about one boy and his dog, well, the boy is like the population parameter, the dog is like the sample average. So what we're saying is that we get an estimate. We don't know what the true population value is, but we can find an interval such that we're confident the population parameter or the population mean lies somewhere within that confidence interval. And if we look at a particular example for confidence intervals when we have one sample, then the confidence interval depends on a few assumptions, and one is that we're dealing with a normally distributed random variable, or else that we have large samples. And the reason we get away with large samples is because of the central limit theorem, where we saw that the sample averages tended to be normal even when the underlying distribution wasn't. And we need independence. And by independence I mean that the result for one person doesn't influence the result for the next person. And in this particular context you would figure that's okay for the Mitchelstown cohort. So then this is our formula. The 95% confidence interval is our estimate. In this context, that's the sample average. It's our estimate plus or minus 2 standard errors. So it's a similar kind of formula to when you're looking at the spread from person to person, except now it represents the spread from one estimate to the next, from one sample average to the next. And so we're talking, instead of a standard deviation, we're talking about the standard deviation of the estimates, and we refer to that as the standard error. 2 standard errors is sometimes described as a margin of error. You'll hear that a lot when people do surveys and they report something on the radio saying the percentage of people who have a certain opinion is, and they give you an estimate, and then they say the margin of error is 3% a lot of the time. And your 95% confidence interval is plus or minus 2 standard errors, so the confidence interval is 4 standard errors wide. This is just a nice illustration. So the value in the middle there is your point estimate. That is to say, it's your sample estimate based on a single sample. And then the confidence interval goes from your estimate to your estimate minus the margin of error to your estimate plus the margin of error. So in terms of where you think the population parameter is, you don't know, but you're 95% sure it's somewhere within a particular confidence interval. This is what you've seen previously. And then a summary. So if you want to get confidence interval in 7 bullets, this is what it is. It's telling you, looking at this, yeah, there's 7 bullets. Looking at this, you estimate something. It could be the sample mean, but it could be something else as well. So you estimate something about the population. You realize that it's only an estimate, so it's not enough simply to tell me that you calculated average moderate to vigorous physical activity and this is the estimate you got. Because it's an estimate, you have to give me an idea of precision. And the easiest way to do that is to give me a 95% confidence interval. That's an interval in which you're confident the true population value lies. Larger samples give you more precise estimates. Larger samples give you narrower confidence intervals. As the variation from person to person increases, so does the width of your confidence interval. But it's hard for you to control that one. But you do control the sample size. So when you're setting up the study, you can decide how large the sample is going to be, and you can be conscious of the fact that the larger the sample, the more precise your estimate is going to be. Now I'm conscious as we go on that this is becoming a very long presentation, so I'd recommend that you stop the video regularly and actually have a look at the notes as well, because they go into this in more detail and they're perhaps easier to read. So what about the effective sample size? Well, we just said that as the sample size goes up, the margin of error goes down, the standard error goes down, the confidence interval gets tighter. So what I want to illustrate now is a situation where you decide how precise the estimate needs to be, and then based on that you decide how many people you need to recruit. And that ultimately is how you should be doing things. You don't want to set up a study, estimate something, get a confidence interval, decide it's not too precise, and then just shrug your shoulders. You need to decide in advance how precise you want to be, and then based on that you need to decide how large your sample needs to be. So I'm just going to look at this example, and I'm going to use moderate to vigorous physical activity, and we're just going to use the standard deviation, which in this case is 163. So let's suppose you wanted to estimate moderate to vigorous activity, the mean value, and you wanted to estimate it to within 20 minutes. So that is to say you want the margin of error in minutes to be 20. Then if you wanted to calculate the sample size, it's given by that formula there. You could play around with the mathematics for the confidence interval and you'd actually derive that relatively easily. So the number that you need is 1.96 multiplied by the standard deviation and divided by the margin of error. Now obviously if you're looking at a population and you don't know the mean, you're hardly going to know the standard deviation either. So the value for sigma that you use you need to have a guess at that. You need to have an estimate based on a previous study as to what you think the standard deviation is going to be. Or perhaps you might make a statement to yourself that 95% of people will lie within 2 standard deviations, and that would give you a sense of what the standard deviation is going to be. So you use an estimate for your standard deviation in this formula. You use a margin of error that you specify. You use the 1.96 because it's a 95% confidence interval. And when you put all that together, it gives you the number of people that you need. So in this particular case here, if we wanted to estimate it to within 40 minutes, we would need 62 people. If we wanted to estimate it to within 20 minutes, we would need 246 people. Notice how it's going up as we want it to be half. If we want the precision to be half what it was before, then it goes up 4-fold. I should say half. What I mean is that the margin of error is falling by 2-fold. And then if we say no, we want it to be even more precise. We want our precision to be within 10 minutes, which is to say when we get our estimate, we want to be able to say that the true value is our estimate plus or minus 10 minutes. Then the sample size goes all the way up to 984. So notice that the sample size goes up exponentially. That has to do with the square root in the formula. So as you want more and more precise estimates, you need more and more people. And that's not surprising, but it's worth noting just how fast that sample size goes up. So in summary then, what have we done? We've defined and interpreted a standard deviation. We've then moved on to confidence intervals. We've looked at the fact that the standard deviation of our estimates is what we call a standard error, and we've related those standard errors to the confidence intervals. And then we've looked at how the standard error depends on the standard deviation, but also on the sample size. And so we've looked at how the sample size is related to the 95% confidence interval. And now what we're going to do next is we're going to extend this where we've looked at the mean values, and we're going to instead look at proportions. So we're going to move on to proportions, and it's actually very similar to what you've seen but for mean values, with one slight difference. So what I have here again is another cut and paste out of Stata, and this time if you look up at the distribution type, then you'll see it's binomial. And what that means is that I'm mimicking a situation where you choose somebody at random and they either have a condition or they don't. Perhaps they're diabetic or they're not diabetic. It's hard to see it there, but p is equal to 0.2. And what that's saying to you is that you're mimicking a situation where you select somebody at random. There's a 20%, or if you like, a 0.2 chance that they have a particular condition. You want to know you want to mimic a situation where you want to estimate that probability. You want to estimate the proportion in people in a population who have a particular characteristic. And what we're doing here is we're getting Stata to simulate that situation where the true proportion is equal to 0.2. And we're looking at a situation then where we take 1,000 samples. And if we look at 1,000 samples, then, and we look at the number of people per sample, and we put that equal to 100. I'm sorry, there's an error on that. It says number per sample equals 1. The number per sample is actually equal to 100. So that's the number that you see up here. So the number per sample is 100 up here. And you have 100 people per sample. You take 1,000 samples. For each sample, you work out what proportion of people have a particular characteristic. And then notice a few things. Notice that your estimate is centered around 0.2, which is where it should be centered at, so that on the average, when you take 100 people and you work out what proportion have a characteristic, it's equal to the underlying proportion in the population, and that's good. But what's incredible is that even though the quantity you're looking at is such that you either have it or you don't have it, when you look at a sample of only 100 people, we're still getting a situation where our estimates are approximately normal. And that means that what we've seen before when looking first at a normal distribution and then when looking at a log normal distribution, we can now apply again. We can now say our estimates are approximately normal, and we can use that fact to get confidence intervals for our estimates. So the formula we're going to use is actually very similar to what we had before. The 95% confidence interval is still going to be your estimate plus or minus 2 standard errors. It's worth pointing out at this stage that this formula, that there is a more precise version of it, and this formula here isn't actually very precise when the proportion you're looking at gets too close to 0 or too close to 1. So you have to keep that in mind. And as I say, there are more precise estimates in this particular case. Precise estimates which are relatively easy in Stata. Now the only difference is this. Previously you would have estimated the standard deviation using that formula that you saw way back, where you looked at first estimating a variance by looking at the deviation from a sample averages and then squaring them and getting the average, and then based on the variance you square rooted it and got the standard deviation. In this particular case, when you're looking at the standard error of your estimate of the population proportion, which is what that p hat is, it's actually given by that formula there. So instead of having a standard deviation over the square root of n, you now have p times 1 minus p over the square root of n. And that's just a feature of this kind of distribution. Clearly you don't know what p is, so in that formula you would be putting p equal to your estimate, p hat. And that gives you the standard error. And then after that, the formula is exactly the same. It's your estimate plus or minus 2 standard errors, so the only difference is the way in which you work out the standard error. So let's try and illustrate that with a particular example. And there's examples again, and more examples actually in the notes. So let's say you want to it says there compare the performance. I'm actually going to do that next session. So let's just look at a situation where you take 50 people, they receive acupuncture, and 30 of them respond successfully as a cure for a headache, which is to say for 30 out of the 50 their headache is cured. And that's based on a sample of 50 people. What you want to know is for people on acupuncture, what proportion of them will be cured as a proportion in the population. So you'd like to calculate a 95% confidence interval for the true proportion, and then having done that, we'd like to interpret our results. So we use this formula here, whereby the confidence interval is our estimate plus or minus 2 standard errors, and our standard error is given by that formula there. Our study estimate is 0.6, that's our estimate of p, so that's p hat if you like. So we put that into the formula for the standard error, and that gives us a standard error of 0.069. And then we simply say, well, if we take our estimate, which is 0.6, and we add and subtract, I've gone back to 1.96 here, we add and subtract 1.96 standard errors, then that gives us a 95% confidence interval from 0.46 to 0.74. So notice that the study estimate, as is to say the estimate based on the sample, 0.6 is bang in the middle of that confidence interval. So what we're saying is that we estimate the population proportion to be 0.6. We estimated that for 60% of people on acupuncture, if that's the right term, their headache will be cured. It's only an estimate, but we're 95% sure the true population proportion is somewhere between 0.46 and 0.74, or if you like, somewhere between 46% and 74%. Now if we talk about the effective sample size, well then it's the same story as before, that if you look at the sample size, then the standard errors, which is a measure of how much the estimates vary, gets smaller for large samples. It's more likely that the sample proportion will be closer to the true proportion as the sample size gets larger. And as a result, the confidence interval is likely to be smaller. The formula that you use is actually very similar to what you had before, except that before we had a standard deviation inside that bracket, squared, and now instead we have our proportion, or more accurately our estimate of the proportion, times 1 minus our estimate of the proportion, and then the rest of it is the same as it was previously. So to give you an example of that, suppose you wanted to estimate the probability of a successful response for those on acupuncture. And let's say I came to you and I said, well look, I don't know what the true proportion is, but based on previous studies, I think it's 0.6. And I say to you, I think it's 0.6, and I want you to get me an estimate of the true proportion. And I want you to get me an estimate so that you can be 95% confident that it's within 0.03 of the true value. That's the level of precision that I'm looking at. Remember that when we looked at this previously with 50 people, the confidence interval was much wider than plus or minus 0.03. So how many people are you going to need? Well, then you simply say it's going to be the estimate that you've been given, 0.6, times 1 minus 0.6, times 1.96, and it's 1.96 because we're talking about a 95% confidence interval, divided by the margin of error, which is 0.03. And then you apply that formula and you get 1024 or 1025, which is about, well, not about, it's 1025 people. It's worth mentioning at this stage that if you don't know what your previous estimate is, if you were to plug 0.5 into that formula, then that's actually the biggest that you can get for the sample size, for the required sample size. So if you wanted to err on the side of caution, then you would put n equal to 0.5 times 1 minus 0.5 times the square of 1.96 over 0.03. And that's basically, if you want to be confident that you have enough people, possibly more people than you need, then you put your estimate of the proportion to 0.5. So I'd make one final point, and this refers to everything that we've seen, both proportions and averages, and that's that the sample size refers to how many people you actually use when getting your estimate. It's not how many people you recruit into the study, so that if, for example, you recruit people into the study but some of them refuse to answer the question, or for some of them you can't estimate their levels of moderate to vigorous physical activity, then you need to recruit more people so as to take that into account. So you'll notice that if you read papers on this, they tend to work out a sample size, but then they also talk about the expected attrition rate, and then they oversample so that they ultimately will have the correct number of people included in their study. So in summary then, this is what we've done. We've looked at the standard deviation for proportions, we've looked at the confidence intervals, and we've looked at how the sample size and the 95% confidence interval are linked together. Now next time what we're going to look at is 95% confidence intervals for differences. So far I've just looked at a situation where we have a population, we want to estimate a parameter. So we want to estimate the average level of moderate to vigorous physical activity for people. We want to estimate what proportion of people are diabetic. But what if we want to estimate the difference in average levels of moderate to vigorous activity for men compared to women? Then what do we do? What do we do if we want to estimate the prevalence of diabetes for men and for women, rather than simply estimating it for one group? So it's important to look at that we go into that extensively in the notes. And the main reason it's important to look at that is because it links very neatly with what we're going to do next week. And I'll leave it at that.